Hello. All right. Let's see. I'm going to plug in my headphones here. All right. So a couple of changes here. Hopefully you were able to get your homeworks done. We have noticed that there's an inconsistency with the progress in the notes so far and the exam date and the homework due dates. This is partly because of the holiday that we had on Monday of last week, and partly because I've been a little slow using the iPad to do the course notes. So we're going to push the midterm exam back. Midterm was scheduled the Wednesday before spring break, and we're going to move it to the Wednesday after spring break. And that'll ensure that by moving it to that Wednesday after spring break, it'll ensure that we get the material done we need to get done to do the exam properly. So Ding is making changes, has updated the CourseWorks page, I think, with those dates. I need to update the course website to reflect that, but we'll push the due dates for the homeworks back a little and the exam date until the Wednesday after spring break. Okay, so I'm going to just dive right in unless there are any questions. Okay. So last time we finished up talking about Lewis dot structures and started talking about group theory, which is the study of symmetry. And you're going to keep doing that here. And I'll say we mentioned that, you know, there are symmetry elements and symmetry operations. An element is a point line or a plane. An operation is what you do around that point line or a plane. It's like we did the inversion operation, which sends all x, y, and z to minus x, minus y, and minus z. And that's sort of like sending the molecule in all positions around a point through that point to the opposite side. There are planes of reflection, and then there are axes of rotation. And we showed how these kind of things can add up. You can do multiple operations in a sequence and represent that with an algebraic type of an expression. And you know, symmetry is really powerful for understanding electronic structure and spectroscopy, especially of molecules with high symmetry, octahedra, tetrahedra, square planar compounds, and whatnot. It's pretty powerful stuff in that sense. So we'll work our way up to it. Today we're going to talk about criteria that define a symmetry group. And you'll see why these are useful. It'll help us build up character tables that you're going to get used to seeing here. One is that it's this identity operation business again. The identity operation is the do nothing operation. And to define a symmetry group, a group of symmetry operations that are characteristic of a molecule, you have to include the identity operation for everything to make sense. Okay, so you have to have one operation that returns all the others. So this is the identity. Okay, and so this statement is basically saying, if you take the identity operation and you multiply it by some other operation, A, it's going to give back A. And it turns out you can do it the other way around too. Turns out, however, it's not always the case that this changing of the order is not is true. In other words, if you have two operations, you can't always flip the order and get the same result. Okay. Not all operations, when done in sequence, will give you the same if you change that order. Okay, so when you have a group, if you multiply two symmetry operations within that group, it has to give you another member of that group. Okay, it sort of makes sense, you know, like it's a collection of operations that define the symmetry of a molecule, and you know, any symmetry operation returns the original configuration. So if you have some other way to get to that configuration, it's also a descriptor of the symmetry of that molecule. So all binary products so if A and B describe a molecule and A times B is equal to some other operation, C, then C also describes the molecule. C is a member. Okay. This is feeling a little abstract, I'm sure. It'll become more clear when we do some examples. Multiplication of operations is associative. In other words, A times B times C is equal to A times B times C. And the last one is that every operation has to have an inverse, which is also a member. So remember, if you have some operation J minus 1 is the inverse, and that product is the same thing as the do nothing operation. It's also true. You have two operations that give you back the identity operation that you can do these guys in reverse. So inverses are, you can swap the order and it doesn't matter. When two operations are not inverses of each other, you can't swap the order, as I mentioned earlier. Okay, so those rules, you got to know them to do some of the exercises on the exams and homeworks and whatnot, and they seem abstract, but they're not too bad, and you'll see as we look at real molecules. All right, so let's do some point groups or symmetry groups. Now I have a handout for you. Let me just go on the website. There's a collection of all symmetry groups for you to look at. And let's grab it here. Oh, it's not there yet. Sorry, I guess I hadn't uploaded it. I don't think I have it on here. Well, I will post a collection of symmetry groups for you to look at. And where is my, I undid it. That's why. Are you seeing my iPad right now? Yeah. Where did you go? Sorry, gotta redo this because I don't see it. Okay. So these are collections of symmetry operations that you can assign to molecules, and the first symmetry group, or so-called point group, is called C1. And C1 is a case where there's no symmetry. Okay. And a sort of simple molecule that fits that description is a chlorofluorobromoform. And if you look at this thing for a while, you'll see there's no symmetry. The only operation is E. So lots of things can be described as C1 because lots of things have no symmetry. People define an order. An order is just the number of symmetry operations in the group. So H equals the group order, or the number of operation. So for this guy, H equals 1. The next one is CS. CS only has a plane of symmetry. And example here, difluorosulfoxide. So this guy has a plane of symmetry that exchanges the two fluorines. So there are two operations here. E and sigma. So H is equal to 2. All right, so we're going to make a multiplication table here to sort of show you how groups are formed. Okay, so for CS, remember, if you take any operations that you see in the group and you multiply them by each other, you have to return another operation within the group. That was one of the rules. So let's see what happens if we try these operations in sequence. So if we do the identity operation times the identity operation, we've done the do nothing twice. And it returns back the same thing. That is equivalent to doing nothing. Okay. What if we did the sigma reflection first, followed by the do nothing operation? What is that equal to? Now, in the example we gave earlier, we labeled these things with a 1 and a 2. So if we do a plane of reflection, we're going to swap the 1 and the 2. And that means the molecule is not what it was when it started. Of course, the positions of the atoms are identical, but the labels have moved. So it's not an E anymore. A sigma times an E is equal to a sigma. And E times a sigma is equal to a sigma. What if you do a sigma twice? What if you do a sigma times a sigma? That sends 1 to the front, and then it sends it to the back again. And that's the equivalent of doing the do nothing. Okay, and so if you see here, this is a complete complete collection of operations for CS. I already told you that, but whenever you multiply the two operations by one another, you get back one of the two operations in the group. No new operations have appeared. So the products of the operations always give back a member of the group. Also, remember that a sigma plane followed by a sigma plane gives you back E, and that tells you that sigma is its own inverse, right? If you do it one operation followed by another operation, and it gives you back the identity operation, that means it's an inverse. All right, let's do CI. CI only has an inversion center. Okay, and the order of this thing is 2. If it only has an inversion center, why is the order 2? Well, it's 2 because you have to also do the identity operation. So let's do this fluorochloroethane. Yikes. You've got this fluorochloroethane in the gauche configuration. And there is an inversion center right in the middle of this thing. It can be a little tricky to see that then when you're doing these exercises on your homeworks and the exams, I really encourage you to think about the molecule in a different orientation. So let's take a look at our molecule by doing a Newman projection of it. Here's our gauche configuration. You can see in this representation, it's a little bit easier to visualize the inversion center. Top hydrogen goes to bottom hydrogen in the back, et cetera, et cetera. So redraw molecules to make it easier to see what's going on there. Let's take a look at, I'm going to jump to a whole new page here. We're going to do Cn, and here n is greater than 1. So these only have n-fold rotations. Okay, so let's do n equals 3, or C3 as an example. And the molecule we're going to work with here is this oxyfluoride of boron. Now these wedges mean that the fluorines are coming out of the page and the other 3 atoms are in the page. This sort of looks like a, I don't know if you've ever seen one of those garden tillers. You know, the teeth are sort of like on an angle, twisting downward. Now this is a C3. So you have to have a C3 axis. You can imagine a axis of symmetry right through the boron, vertically oriented, orthogonal to the paper. This guy, C3 axis only, and it sends fluorine 1 to fluorine 2 to fluorine 3. Just to be clear, there are no mirror planes here. Right? If the fluorines were in the page, then you could have a plane of symmetry in the paper. But if you reflect about the paper, in this case, the fluorines on top are going to go below the paper, and that's not the same orientation. All right, so let's do a multiplication table for this guy. Okay, let's start off by just adding our C3 and our E. Now, we all know if you do E times E, you get E back. That's not a big deal. C3 times E, you're just going to get C3 back because the E did nothing. E times C3 is going to give you C3 back. What if you do C3 twice? Right? If we were to label these 1, 2, 3, and then we pay attention to this fluorine number 1 here in the upper left-hand corner, and we do a C3 followed by a C3, it's going to send fluorine 1 into this position. That's not what we started with. So if we do C3 2 times in a row, we get a new orientation. And that means that there must be some other operation that sends fluorine 1 all the way over to fluorine 3 that's also a member of the group. Right? Any binary products have to be members of the group. So C3, C3, what sends fluorine 1 all the way over to fluorine 3? Well, it turns out it's C3 twice, which is sort of boring. but C3 twice is its own operation. And we have to add it to our table now. Okay. So now if we do C3 twice times E, we get C3 twice. E times C3 twice. It's fine. C3 twice times C3. That's just like doing 3 C3s in a row. That gives you back the identity operation. Same if you do it in the other order. What if you do C3 twice? We're going to send fluorine 1 here, and then we're going to send it all the way over here. We do C3 twice. That's equivalent to just doing a C3. We fill out our table, and you can see we got them all. Okay, so C3 twice must be a member of the group C3 times C3 is C3 twice. C3 must also be a member. Okay. Let's jump to our next one here, CNV. These are very common. What's CNV? CNV has a CN axis and N mirror planes parallel to CN. My PhD advisor used to say, when in doubt, just guess C2V. C2V pretty common. Molecules that are C2V or CNV kind of point like arrows. Sulfur kind of points like an arrow upward here with its 2 flanking hydrogens. There's a C2 axis that swaps the 2 hydrogens here. And according to our definition, we must have 2 mirror planes parallel to CN. Those guys look a little something like this. Got your C2 axis here. Now 2 mirror planes. This one here is what's called a sigma V. Sigma V denotes that it is coincident with the CN axis, or what's called the principal axis. Why V? It's V because it's sort of vertically oriented. You know, so the principal axis is often drawn up and down. And what's this other one called? Well, this is also a sigma V, but it's given a different denotion. It's denoted with a prime. And the reason is that it does not contain the atoms, right? Hydrogen sulfide here is going to sit on the sigma V and not the sigma V prime. So prime and double prime, as we'll see later for other point groups, indicates lower priority. The higher priority label goes to the plane that contains the atoms rather than the plane that bisects them. Now, some of these conventions, as you're going to find, are not the same as what the book is using, and one book will be different than another book, and it can get a little bit confusing. But the primes are, we're going to stick with this idea that the atoms fall in the plane of the primary plane, does not have a prime, and prime is given when the atoms fall off that plane. All right, so I'm going to jump down here. And we're going to do some of these operations. So let's take a look at sulfur. Give these guys some labels. Let's see what happens when we do a C2. So C2 is going to swap these two hydrogens. Sends B over to A and A over to B. Let's do a sigma V here. Sigma V is going to send sulfur A and B back. Nope, sorry, got that screwed up. I got ahead of myself. Right, sigma V, what does sigma V do? So sigma V is the one that has the atoms in the plane, and it sends the front of the molecule to the back and the back of the molecule to the front, which you don't really see here.
Professor, can I ask a question?
Yeah.
If it doesn't really show that H and B are coming in and out of the page, can you use the lone pairs that exist on that molecule to show the orientation or to imply it? Like put the lone pairs going into the page or out of the page to imply
Yeah,
that, like,
so that's a nice way to think about it. Or you could think about the atom as being a sphere. You know, in the front of the sphere and the back of the sphere would be exchanging. The positions of the atoms is the same. But if you think about them as spheres, the front and the back are exchanging. So it doesn't really change the symmetry, but some molecules might have more parts than just these three atoms. They might have a front and the back, and you would be reflecting that front and the back here. And you just don't see that in this particular example of C2V. So this C2 followed by a sigma V, there's also an operation that takes this molecule as drawn in the upper left and puts it down here. What operation is that?
Sigma V prime?
Yeah, it's sigma V prime. Now, sigma V prime is not the same thing as C2 here. Or in other words, if you do C2 followed by C2, this is not equal to sigma V as another one. for the reasons Mac was asking about, you know, the lone pair is coming, the spherical part, the spherical shape of this molecule being exchanged in front and back. You know, when you do a C2, the front of HB on the right-hand side becomes the back of HB on the left-hand side. Okay, see, if you do two C2s in a row, that's not sigma V because of that front and back exchanging stuff. Sigma V. Right, C2 twice is really E. So in other words, sigma V is not the same thing as E. All right, let's do a multiplication table. C2V. We're gonna get an E, we're gonna get a E, we're gonna get a C2, we're gonna get a C2, we're gonna get a sigma V, and we're gonna get a sigma V prime. Okay, E times E is easy. E times C2 or sigma V prime is easy. So now we do the interesting ones. What if you do C2 twice? C2 twice is the same thing as E. And what if you do sigma V twice?
You get E. It
Also
should
an
be
E.
E all down the diagonal, right?
Sigma V prime is also an E. Planes of reflection are their own inverses. So you're going to get E's in those positions. All right, so we did just a minute ago C2 followed by sigma V and concluded that it's the same as sigma V prime. And what if we do them in the other order? It's going to give you the same thing. And if I did a sigma V prime first followed by a C2, you're going to get a sigma V. And so on. And what about sigma V followed by sigma V prime? So let's do one of those. So we're going to reflect the molecule in the front and the back first for a sigma V, and then we're going to reflect the left and the right for a sigma V prime. So let's pick a point on the molecule. Let's take this hydrogen, for example, over here. Let's pick a point behind it. So if we do first a sigma V is going to send the point behind it to the point in front of it. And now if we do a C2 and we send the point in front of it over to the other side, it's now going to be behind it. So the point behind it became the point behind it on the other side. That's the same thing as reflecting about sigma V prime. Okay. So let's do the same thing now. We're going to take this point behind it we're going to do sigma v. And now let's do a sigma v prime. So the point behind it is going to the point in front, and now it's staying in front and going to the other side. That's the same thing as taking this point and swinging it over here with the rotation. That's a C2. Now, stuff like that can be tough to visualize. And I'm going to just stick these C2s here. One of the things that you might consider doing is getting yourself a model kit. You know, you can get model kits on Amazon for 20 bucks. And if you don't have the money and you really want one, I'll give you one. Okay, if I can. You know, sometimes some people are better at this than others. Everybody struggles. And, you know, you're just going to have to try and push yourself to get used to doing it. The more you do it, the easier it gets. So go try lift some weights, recreate this C2V multiplication table, or do the one in your homework set. You know, if you can't do this stuff easily, life's going to get harder down the road. So I'd encourage you to put some effort into practicing here. Okay, so E, C2, sigma V prime. The products of all those give back members are the same. So we're good. Let's take a look at another one. Here, I'll just leave that up for you guys to see while I work on number 6. C and H. These guys have a CN axis and one horizontal mirror plane. That is orthogonal to the CN axis. These are tricky. It's hard to recognize them. Let's do an example here, C2H. They all kind of look like this. They're often planar. And they have this kind of like screw look to them. You know, it's almost like a propeller or something like that. They've got like a spiral sort of a shape to them, but this one's flat, you know, top and bottom, above and below the paper is the same. Let's draw this guy slightly differently. So you got a sigma plane here. This guy is a sigma H. Where's the principal axis? Principal axis is right in the middle of the molecule, orthogonal to the paper on this left example. And it sends fluorine to fluorine or hydrogen to hydrogen with a 180-degree rotation. So, you know, the paper in this example here contains all the atoms. So there's a plane of symmetry in the paper, and that plane of symmetry is orthogonal to that C2. Now, anytime you see an H, when you're looking at point groups, you know you have a horizontal plane of symmetry. That's a pretty useful thing to remember. You'll get used to this. There's not that many of these in the end. The H is really valuable. The H tells you you've got this plane of symmetry that's orthogonal to the principal axis, okay? Let's do the point group or the multiplication table here for C2H. E times E, C2, or sigma H is going to give back the same. C2 times C2. I'll draw my molecule over here again for reference. Right, C2 sends F1 to F2. Do it again, F2 goes back to F1. That's the same as doing nothing. Sigma H, sigmas are their own inverses. How about a C2 followed by a sigma H? We're going to send C2 F1 to F2. The top of F2 to the bottom of F2 after that sigma H. How do you get the top of F1 down to the bottom of F2 here?
Is that an inversion?
That is an inversion. A little bit hard to see, but let's think about it this way for a second. What is the definition of an improper rotation? An improper rotation is a rotation followed by a reflection through a plane orthogonal to that. And so anytime you have a sigma H, you're going to end up with an improper rotation. And when it's a C2, that's the same thing as an inversion. So an inversion is the same. Oops. Inversion is equal to C2 times sigma H, which is the same thing as S2. Okay. The C2 followed by sigma H gives you an I in here, and also back there. So we could add I to our table. And we know E does nothing, so we can write I's in there. So let's do an inversion followed by a C2. Well, that's just going to give you a sigma H. C2 followed by inversion is going to give you a sigma H, and so on. And I followed by I is the same thing as E. If you have a hard time doing the inversion center in your head, one way to make it easier on yourself is to remember that C2 times I is the same thing as C2 times C2 times sigma H, right? I is C2 times sigma H. So you could break that I out, unpack it, and make it into the C2 times sigma H, and now it's a little bit easier to do this. Right? This gives you back sigma H in the end. The C2 times C2 is the same thing as an E. Okay, so I is a little bit tricky, but if you use the algebra, it gets a little more straightforward. All right. We're going to do some D's here. dn defined by a Cn axis. It also has n C2 axes perpendicular to Cn. Or the principal axis is maybe a nicer way to write that. Let's write it that way. So, favorite example here. Let's take this cobalt compound. Kind of like a Newman projection, but now we're looking down there at that one cobalt from which you've got 3 staggered things. And I'm going to put these fun little petals around it. This is meant to be a representation of an ethylene diamine complex of cobalt. Where's the principal axis in this molecule? It's probably going to go through the cobalt. You can see how the nitrogens on the top of the page might jump to the nitrogens on the other parts of the top of the page here by rotation. So I can see a C3 axis there that exchanges these 3 and exchanges these ones in the back also at the same time. And let's look at this petal. So this arch here goes from here to there. Yeah, there's a C3 axis. In and out of the page. That's the principal axis in this molecule. This guy is D3, it turns out. So we got a C3 axis, and now we should have 3 C2 axes perpendicular to the principal axis. Where are those? So principal axis is here. Plane of the paper is orthogonal to it. So any C2 axis we're looking for is going to be in the plane of the paper. And you got to have 3 of them. So they presumably line up with these petals. Let's draw this one here. This is a C2. And you can see how it sends the nitrogen on top over here to this one on the bottom. And it sends this nitrogen on top all the way over to this side on bottom. This guy becomes this guy. So this is like a 3-fold propeller, right? And it sends one propeller leaf to the other propeller leaf's position. And then it just rotates this propeller from top to bottom. And there are 3 of those. Okay, so the highest order axis in this molecule is the 3-fold axis. That is the principal axis. No mirror planes here. It's tempting to find a mirror plane, but there are no mirror planes. So how many operations in this group? We have E, we have a C3, we got a C3 twice, and a C3 3 times, oh, sorry, which is the same as E. So C3 and C3 twice. And we have 3 C2 axes perpendicular to Cn. And those C2 axes, which are perpendicular to Cn, are going to be given a prime designation, C2 prime. The perpendicular axes are given the prime designation. And there are 3 of them. So I count 1, 2, 3, 4, 5, 6. H equals 6. All right. Next, we're going to do D and D. Again, we've got a CN axis, NC2 axes perpendicular to CN. And now we're going to have some sigma Ds. In fact, N sigma Ds. What's a sigma D? Sigma Ds are mirror planes that bisect the N perpendicular C2 axes. So let's draw it out so you can see it here. And I'm going to do, as my example, D2D, the famous D2D. We're going back to our old friend Aline here. Shall I say, our soon-to-be old friend Aline. Let's give us some labels: A, B, C, D, clockwise fashion. Well, it's not too hard to see that you can have a C2 axis here that exchanges B and A and C and D. That kind of makes sense. Just a little note here. The principal axis usually contains the most atoms. You might be forced to choose on occasion and choose the one that goes through the most atoms if you have to. All right, so there's this C2 axis that defines D2D. Now we also need N perpendicular C2 axes, and we need some sigma Ds. In fact, we need 2 of them. Let's take a look at those. It's going to be a little tricky to see here. Where are those perpendicular C2s? Well, the C2 axis skewering the 3 carbon atoms is your principal. So you've got to have some axis that's perpendicular to that. So it's going to be some axis that runs through the central carbon and is in some plane orthogonal to that C2. Where are those? Kind of tough to see. How do you rotate this thing? So I'm going to choose one here. I'm going to send this guy over to this side, and I'm going to send this hydrogen here over to this position. I'm going to send B to D. And so I can't really illustrate it to you, but it's This guy is orthogonal to the paper, that's CD bond, CHD, the CHB is in the plane. So it's 45 degrees, you know, in between those two hydrogens that will swap the B and the D and the C and the A. Can't really draw that too easily. Let's just draw it out like this. I said B is becoming D, C is becoming A. And where is the other one? Well, the other one's going to be 90 degrees away from that one. So this can be hard to see, but let's take a look with a Newman projection. I'm going to put my C and my D here. Let me make sure I get these right. So put A and B there. Suppose it doesn't really matter. Yeah. All right, so we're looking down the principal axis here, right? We got a C2 axis exchanging D and C and A and B. But then we can put some C2 axes in here. And so if we rotate about this one, let's say, going through that central carbon, it's going to send this HD over to that guy, or this B to that C. Really helps to have a model of this molecule. All right. Now, what's the other piece of this? What's the other symmetry operation we need here? Anybody see one? We haven't done? We did a C2 and two C2 primes. What else is here?
Sigma D.
Sigma D. We got to have some sigmas. Where's the sigma? Where's the plane of reflection? Well, the plane of reflection goes through here. Reflect the top and the bottom, or the left and the right. All right, let's do another one. Let's do D5D. So I said there's got to be a C5 axis here, right? Because it's a D5D, which means we need 5 perpendicular C2s and we need 5 sigma Ds. So what does that look like? Well, classic example is ferrocene. in the staggered configuration. Let's do a C2 operation here. And we're going to take a look at this thing from the top. Too bad there aren't shapes. Now, it's staggered, so the points of these pentagons don't overlap. They're kind of in between each other. And now we're looking for, it's not too hard to see the C5 axis, right? C5 axis just sort of spins the ring around. But what about these perpendicular C2s and 5 sigma Ds? Well, here's one of my sigma Ds. Iron is right there in the middle. Here's a sigma D. That plane of reflection sends the atom on the bottom left and bottom right and swaps them. So these two get swapped. And you can do this sigma D in 5 different orientations. Just pick the various points of the points of the pentagons here. Work your way around. All right, how about perpendicular C2s? Perpendicular C2s, they're going to go orthogonal or perpendicular to the principal axis. The principal axis, of course, is right in and out of the page. So these perpendicular C2s are going to run through the iron center, and they are going to send, for example, this carbon here to this carbon's position. They're going to send the bottom half to the top half, one point to the other point. And the C2s and the sigma Ds, turns out, bisect each other. So they go exactly through the crevices here. There are your perpendicular C2s. There's another one. And those guys send this point down to this point. Or as we said, this point down to this point. Or this point over here. Not a very neat drawing. I'm sorry, I'm not quite as good with this thing as I am on a chalkboard. Stone hands. All right, so notice how the C2s bisect the sigma Ds, okay? So I haven't drawn in all of the sigma Ds. I could go nuts drawing lines on the page here, but take a look at this one, this sigma D. He's got a C2 over here and a C2 over here. Another sigma D would be here and here. The C2s bisect the sigma Ds. Okay, so let's do all the operations. How many operations do we have? So we got an E, we got C5, we got C5 twice, we got C5 3 times, we got C5 4 times. We have 5 perpendicular C2s. we have 5 sigma Ds. Anything else? Anybody see something else?
Do we have an inversion center as well?
Good call. There is an inversion center. Now, it turns out, remember, inversion centers are rotations followed by reflections. There's no horizontal plane of reflection in this molecule. And that should tell you there's probably more stuff hiding. So there's an inversion center. It sends each of the points to the opposite side. So boom, 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 etc. Another way to do this, actually, interestingly, is you can take this guy, rotate it to this position, and then reflect about a plane orthogonal to that and put it into this position. That's an improper rotation. Or I could go 1, 2, 3 and reflect. So I could send this carbon over here to this carbon. Or I could rotate this guy all the way over here and reflect. That's the inversion. That's a C2 operation we just did, right? That's 180-degree rotation. So it turns out this guy has what's called an S10, an S10 3 times, an S10 5 times, S10 7 times, S10 9 times. What's an S10? So let's just do S10 once, right? S10 once says rotate 1/10 of the way around. Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. So I'm gonna go 1/10. There's my C10 rotation. Orthogonal reflection sends me to this position. Let's do S10 3 times. Once sends me here, twice sends me there, 3 times sends me here. Okay. Now where's this inversion center? Oops. The inversion center turns out is the same thing here. S10 5 times is the same thing as an I. Let's just do that really quickly. We're going to go 5-fold rotation. 1, 2, 3, 4, 5, followed by reflection, sends this point to this point. That was our inversion maneuver, right? That's an S10 5 times is a 5-fold, sorry, is half the way around. That's 180-degree rotation. So that's your I. All right, so total operations, H is equal to 20 for D5D. Okay. Good. So that's what we have for today. We're almost through the important ones. And we'll pick this up next time. And anybody that wants to stick around and ask questions is welcome. I have time to do that with you now. So the rest of you can sign off and I'll put this up on the website soon.
Thank you.
Yeah. Okay.
I don't think I have any questions today, but I'll see you guys next class. Thank you.
Terrific. All right, Mac. See you soon. All right, then you can stop recording.